For temperature and humidity sensing, we have two different modules. One that collects the internal temperature and humidity of the house using sensors, and a second module that collects weather data using the data from the Weather Underground API. The data collected through the Weather Underground API include external temperature, relative humidity, wind speed, and general conditions like windy, dusty, fog, smog, and etc. The Weather Underground API also provides pollutant information, but unfortunately that data is not available for Turin. The collected data from these modules is then published using MQTT.
Let's now talk about dust part. We have an internal sensor and an external sensor. They publish data and the dust decision maker receives them thanks to the MQTT protocol. The decision maker receives via REST the thresholds set by the user and publishes two values. One indicates if it is necessary to clean the air, instead the other one is a mark for the air quality outside. So it points out if it is a good idea to open the window. We have to notice that the sensors are simulated, so the internal one subscribes in order to receive data from the outside one. In fact, it varies its data depending on the outside. In practice, this connection should not exist because the two sensors are independent. The decision maker uses two thresholds to take decision. The internal one is used to point out if the air in the house needs to be purified. The external is higher and it is used to assign a score for external air quality. The gas sensor should send the detected gas value, but our sensor cannot sense this value. It can just detect if a variation of the gas level occurs.
When we are saving energy, we don't want the system working if there are no people inside the house, or at least if they're not coming home anytime soon. For this reason, we have developed two modules, a motion sensing module and a motion prediction module. The motion sensing module simply detects if there are people inside the house or not, so it can tell the central controller and help him make the right decision about purifying the air. The motion prediction module, on the other hand, based on historical presence, predicts whether there will be people inside the house in the next time instant, let's say in the next half hour. Then it reports this value to the central controller. Having both these values in mind, as well as many others, the central controller makes a decision about whether or not and how to purify the air.
And relative humidity decision-making module subscribes to the topics of the sensing and the Weather Underground API modules, and using the information calculates a score between 0 to 5, which basically says how good of an idea it is to open the windows based on the internal and external weather conditions. A score of 0 says don't open the windows now. A score of 5 says it's really good conditions to open the window now. Then this score is published using MQTT. The actuator subscribes via MQTT for the decisions of the central controller and also to another topic for the vacation mode. The actuator is connected directly to the relay circuits that control the window and the air purifier and implement the decision of the central controller, except under one scenario, the vacation mode. A user can turn on vacation mode using Telegram, and when this is done, the actuator overrides the decision made by the central controller and keeps the windows closed and the air purifier stopped, and again except in one condition, in the case of a gas leak. The central controller subscribes to 10 different topics from both the sensing and the decision maker modules, and based on a predefined weighted model for the scores from the different modules, makes a final decision on whether to open the window or to run the purifier or to do both or neither. This final decision is then published over MQTT. It also acts as the module that uploads the data to ThinkSpeak using REST.
The Resource Catalog user interface is a module deploying REST communication between the Resource Catalog web server and the Threshold web server. It allows the admin to both add a new house to the system and to modify an already existing house informations, updating the Resource Catalog. The Threshold web server and user interface is a module deploying REST communication. It manages the house's threshold values in the system. In particular, it provides these values to different modules, and it also deploys a graphical user interface, through which the user is able to modify threshold values of his or her own house. This module manages also the MySQL database communication, for checking if the login data inserted by the user accessing the setting page are correct. The Telegram bot deploys both REST and MQTT communication, and through specific commands, it consents to the user to retrieve live information about the house status and to set the vacation mode.
The Raspberry Pi is connected to the internet through the Ethernet cable over here. Then we have all the sensors connected to the Raspberry Pi, like we have the motion sensor here, which is connected to the Raspberry Pi. We also have the temperature and humidity sensor here, which is again connected to the Raspberry Pi. And we also have the gas sensor, which has a digital output connected to the Raspberry Pi. And once all this goes in, we have the decision making. And once the decision making algorithm works and makes a decision, it has two things it actuates. One is the window, which is being simulated here by this particular LED, which will glow on when the window is open. And the other is the purifier, which will be controlled by the relay network here, which has the resistors and capacitors, which will then forward the information to this particular relay. And then when this relay switches on, it will get the main supply from here, and it will run the purifier here, which will then clean the house.
In this section, we present the action performed by the admin through the resource catalog interface. Through the user interface, the admin logs in with his credentials. These are verified by the threshold web server using a REST communication. Once the admin is authenticated, he will have two options available: adding a new house or modifying an already existing one. Firstly, a new house is added by the admin. The Add House page lets the admin specify all the necessary infos to insert a new house in the system. Once everything is done and the Submit button is clicked, the new home is created. The informations are sent through REST to the Resource Catalog web server, which will add the new house entry in the Resource Catalog using the just entered data. The admin is then redirected to the login page. The other operation the admin is able to perform is to modify the information of an house that's already inside the system. The admin again has to log in, and like before, the same authentication procedure is applied. Through the drop-down list populated retrieving the house IDs from the Resource Catalog web server, he selects the house he wants to modify. The form is then filled with the selected house data, again retrieved from the Resource Catalog web server. He can modify the fields related to that house and then submit the new informations. Using REST, the selected house info are sent to the Resource Catalog web server, which will update the Resource Catalog. The user is able to set the sensor thresholds through the specific interface. Each user has his own credentials to access the setting page. This page allows the user to check and modify the thresholds and access the freeboard panel. Once authenticated, the form is filled, retrieving the informations from the threshold web server. The user can eventually modify the threshold values. Submitting the form, the new values will be communicated to the threshold web server through REST, updating the threshold's values.
Here you can see the motion prediction module running on a PC and how it communicates through MQTT with the motion sensing module running on the Raspberry Pi. As you can see on the small Raspberry Pi command prompt, motion is detected every 3 seconds and remembered in a dictionary. When the counter reaches 10, all these values are processed and the module decides whether there was presence or not. Based on this decision, it publishes 1 or 0, 1 if there was presence and 0 if there was no presence. On the bigger screen, you can see the motion prediction algorithm. It receives values for presence from the motion sensing module and sends values for predicted presence to the central controller. All of this is done through MQTT. You can see how the motion prediction module successfully receives every publish of motion and appends the value to the week list. The algorithm later uses this list to calculate the new predictions. At the end of every week, the predictions for next week are calculated. Even though they are all calculated at once, they are published every half hour. Basically, every half hour the central controller receives one value for the current motion and one value for the predicted motion for that time instant.
Now we are going to show how the system works in different situations. The dust sensor simulators will run on the Raspberry, while the dust decision maker will run on a laptop. The black window on the top will be the external sensor. The other black window will be the internal one. The white box in the bottom will be the decision maker. The laptop will notify all the data received and all decisions taken by the central controller. In the first scenario, the dust level inside is good, the outside dust level is bad, the internal temperature is supposed to be good. In the dust controller window, we can notice that the internal dust is under the threshold and the outside dust value is higher than the threshold, so it publishes 0 in cleaner field and 0 in window field. On the laptop, we can see the decision taken by the central controller. In particular, the window is closed and the purifier is off. In the second scenario, we have a bad dust situation inside and outside. The central controller decides to switch on the purifier. We have to notice that even if the outside temperature is very low, the temp decision window field reports a good score. This is due to the fact that temperature is a real value provided by Weather Underground, and we manage threshold in order to record these situations. So let's focus on temp decision window field. In the third scenario, we start from a situation in which external dust level is high and internal air needs to be purified, so the purifier is on. Let's now assume that something changes in weather and external dust decreases, let's say thanks to the wind. We simulate it changing dust level in external simulation. The central controller switches off the purifier and opens the window. In the fourth scenario, the gas sensor detects a gas leak. Even if external dust is bad and internal one is good, the central controller opens the window and turns the purifier on. The Telegram bot notifies the user about the gas leak. In the fifth scenario, we have to focus on the temperature. Since the internal dust level is bad and the external dust is good, initially the window is open. But due to a change in temperature, the central controller switches on the purifier and closes the window. In the previous scenarios, the prediction value or the motion value were positive. In this scenario, prediction value is 0, and we put motion sensor inside the box in order to don't predetect presence. So, even if internal dust is higher than the threshold, the central controller does not clean the air.